Boa tarde. Olá. Boa tarde a todos. Bem-vindos a esta palestra, Próxima, Paragem, Universo. Vamos ser levados aqui por uma viagem do outro mundo, esperamos nós. Eu sei que há muitas pessoas ainda a chegar porque houve aqui alguns cortes de estradas à volta do pavilhão, por isso não se estranhem se houver pessoas a tentar interromper. Este evento que celebramos hoje é o evento de abertura da Semana Mundial do Espaço. A Semana Mundial do Espaço celebra-se todos os anos, por todo o mundo, de 4 a 10 de outubro. Todos os anos, cerca de 100 países fazem esta celebração, sendo a maior festa de astronomia e de celebração do espaço. Aqui em Portugal, a Ciência Viva organiza vários eventos, aqui no pavilhão, mas também em todos os centros de Ciência Viva. Aqui vamos ter hoje esta palestra, Próxima, Paragem, Universo, com o Mark McCaughrean. Teremos também amanhã outra palestra com o Rui Moura, que também já está aqui presente, por isso se tiverem questões, convido-vos a fazer depois da palestra sobre a exposição que temos no nosso átrio, Engenhos do Espaço. E também teremos, no fim desta semana, a Conferência de Professores Espaciais. Estou a ver aqui algumas caras conhecidas, temos aqui algumas pessoas entre nós. Espero ver-vos também novamente na sexta e no sábado, aqui a participar nas nossas palestras e workshops para professores. Além disso, organizamos também por todo o país, em escolas, com a parceria da indústria, da academia e de laboratórios, o Espaço vai à escola, que é uma atividade que traz investigadores e especialistas ligados à área do espaço às escolas da sua localidade ou outras, e é uma atividade que chega todos os anos a cerca de 20 mil alunos. Isto é uma celebração nacional, global, e ainda bem que estão aqui connosco para celebrar isto. Chamo agora ao palco João Linhum para fazer a apresentação do nosso orador.
Ora, boa tarde. Eu vou fazer a apresentação em inglês. Okay, so when I was asked to present Mark, I was tempted and checked what the AI was saying about Mark. But then I decided, no, I prefer to draw from the many years that I've known Mark for. I first met Mark in 1991 in Arizona. I was a PhD student in Boston, and I was in Arizona observing using infrared array detectors, the technology that the Rika's couple, George and Marcia, were developing. Those were the roots of the modern infrared astronomy, and Mark was their PhD, their postdoc, I believe. So I would also like to mention that the impact of these array detectors, and during those years, I believe the Rikas and Mark were among the few astronomers who had access to this kind of detectors and knew how to use them. But they laid the groundwork for this new technology that enabled this tremendous scientific development and impact of infrared astronomy. Now, after that, Mark returned to Europe, and he has been working in different universities, scientific institutes. He kept involved with all major developments and applications of infrared astronomy, with a presence in the scientific boards of the Hubble Space Telescope and the James Webb Space Telescope. Until last year, he was a senior advisor for science and exploration at the European Space Agency, ESA, and he's currently an adjunct scientist at Max Planck Institute for Astronomy in Heidelberg. As an astronomer, his main field of research is star formation, which is also my field of research. That allowed us to collaborate, especially in the framework of European research networks, where he proved to be a strong defensor of European collaborations and an excellent research coordinator. He's also one of the best science communicators I've ever met. For many years, his talks were well known to be fascinating and very engaging, showing spectacular images. Now, the human face of science is something that Mark cherishes a lot also, and he's a co-founder of Space Rocks, which celebrates space exploration and its connection to art, music, and culture. Now, I'll tell you a secret. He's very fond of Portuguese grilled fish. Many years ago, once, he had me drive him to Setúbal just to eat this fish, and I can tell you, it was the freshest fish I ever had till then. And I never got to really thank him for that. So we are really lucky and pleased to have Mark with us today and give his talk, Next Stop, Universe.
Took me for fresh fish yesterday, but not in Setúbal, in Sesimbra, so I will have to compare the quality of the fish. So let's see, if you can switch to my presentation. Up there in the regie. Very good, yes. Thank you very much, and I've been here before, and it's always a pleasure to come back to Portugal, and also to the pavilion here, and thank you to everybody who's here, but particularly to Katia, who you just saw a moment ago. She worked with me as a PhD student, and she learned everything I knew, and now knows much more than I know, which is a good thing. So, as João pointed out, I currently work in Germany, and I used to work in the Netherlands, and I've worked for a very long time on the James Webb Space Telescope. And I've worked with many space missions over the years, and what I want to show you today is a little bit of a selection of some pictures from space missions and some stories as we go through the universe. And because I am now retired from the European Space Agency, I'm allowed to sell a book to you. So if you would like to see more and read more about some of these destinations, this book will be outside afterwards. But let's start in Germany, where I currently work. This is the Max Planck Institute of Astronomy on the Königstuhl, high above the city of Heidelberg. And this lovely building here on the left wasn't there. I used to work here in the 1990s, and I came back, and this lovely building is for outreach. It's shaped like a galaxy, and it's got a planetarium. And if you're ever in that part of Germany, I very much recommend coming to the House of Astronomy there. Heidelberg, of course, itself is a very beautiful city, maybe a little bit colder than Lisbon in the winter, as you can see. The Institute is in the fog at the top of the hill there. But before that, before I moved back to Heidelberg, as was pointed out, I worked at this place. This is the European Space Agency's technology center, ESTEC, in a place called Noordwijk on the Dutch coast. And you can see just how close to the sea there, the North Sea. And this is where Europe brings all of its space missions together, tests them in various ways before they get taken to South America and then launched on rockets from Kourou in French Guiana. So I spent a lot of time working here. You can see ESA has certain strange things about it, like it has its own golf course in the foreground there. But the thing about the Netherlands is it's a very, very flat place. Not quite like Portugal. So this is the typical area. This is a bit north, actually, of Amsterdam. But this is a very typical kind of old area of the Netherlands where there's lots of canals and rivers and lakes all joined together. And I spent many, many, many hours cycling around this area of the Netherlands. So this is the Hook of Holland at the bottom here. I think I have a pointer. This is where the ferries go to the United Kingdom. This is Amsterdam here, The Hague, the capital of the Netherlands, well, actually here, and then the European Space Agency right on the coast. And these are all the ways I cycled. And Pedro in the audience, Pedro Russo, he has cycled many of the same ways. Maybe he's younger than me, but he hasn't cycled quite as much as me. So he has a bit to catch up. This is all my cycling from 2012 in the Netherlands, 101,000 kilometers. But here's the interesting fact. The total amount of elevation I gained was just 100,000 meters. 100,000 meters. So that means the Netherlands is flat to 0.1%. It is very flat. Most of the elevation was going over bridges, over the canals, and a little bit in the dunes. But the reason I'm showing you this is because, of course, human beings are small. We're 2 meters or so, and the Earth is very big. And when people tell you the Earth must be flat, some people, if you lived in the Netherlands, you would believe it. Because why would you think the Earth is curved at all? The Earth is indeed curved, but so much bigger than we are that it's almost impossible to appreciate that curvature. And as human beings spread around from Africa, moved into Asia and later into Europe when the glaciers receded, further down into Australia, to Polynesia, and then into the Americas. At this point, of course, when this was frozen, the Bering Strait between what is now Russia and Alaska, you could walk across here, and that's how people spread across the world. But they were walking. Maybe they took the occasional boat, like these Vikings here, but to some extent, everybody still thought the Earth was flat. Now, the ancient Greeks before this worked out from doing astronomy and doing measurements of the angle of the sun and shadows cast on the ground. They worked out that the Earth must be actually round, but nobody had seen that. You can see a little bit if you live here in Lisbon and you watch ships sail out to sea. They slowly disappear below the horizon because the Earth is curved. So if you see a big cruise liner or a big yacht with a big mast, it will appear to be descending as it goes away, and that's because of the curvature of the Earth. But to see it, you really need to go above the Earth. And so in 1903, this was the first aeroplane flight, powered aeroplane flight. This is at Kitty Hawk in the United States, in North Carolina, and these are the Wright brothers with their first ever powered flight. It went less than 100 meters. And it didn't go very high, so obviously they couldn't see very much of the curvature of the Earth. But only 58 years after that, things changed, because the first human being went to space. And that human being was Yuri Gagarin in April 1961. I was born 20 days before that, so I have not lived all of my life in the space age. Many people in the room are younger than me. You've lived in the space age. There have always been humans who have been to space. And of course, the first woman to go to space was only 2 years later, and this was Valentina Tereshkova, also from the Soviet Union. So these astronauts were the first people, or cosmonauts, were the first people to see the Earth from far enough up that you could begin to see it as a globe. Aeroplanes had gone high, and we'd been able to see that, but the astronauts, the cosmonauts, went hundreds of kilometers high and saw that. Now, here's the interesting thing. Gagarin did not have a camera on board. There are no pictures taken from inside Vostok 1 of that first flight. He was busy wondering whether he would die, I suppose. He came down after one orbit, but there were no pictures taken. The first person to take pictures was Titov on the next flight. But a few years ago, astronauts on the International Space Station kind of recreated what they called Yuri's view. The Earth as Yuri Gagarin and Valentina Tereshkova and the other early astronauts, cosmonauts, would have seen the Earth. From a few hundred kilometers up, you can clearly see that this planet is now curved. You see the sun illuminating the clouds. You see shadows cast. So this beautiful view, Gagarin was the first person to see that. But by now, many hundreds of people have shared that experience, and a great majority of them have seen it from the International Space Station, which you see here. This, of course, has been in orbit for more than 20 years, has been built up over many flights of the space shuttle from the United States, from some rockets from the Soviet side, the Russian side later on. And you can see this Japanese module here with the flag. And this is the European module, the ESA module on board. So there have been many European astronauts on board as well. And they're a bit more comfortable, perhaps, than Gagarin and Tereshkova were. So this is Samantha Cristoforetti, ESA astronaut who has had 2 6-month stays on the space station. And now, of course, it's a shirt-sleeve environment for doing science, mostly. There's a big science lab on board. But they have some free time to look out of the windows, which is a very, very lovely thing. I'm going to share with you, because this is the introduction to the talk, I'm now going to share with you 1 minute of film, what it would be like in real time if you were looking out of the window with Samantha. And you need to turn the sound up, please. Or alternatively, not turn the sound up. I'll comment, this is the Straits of Gibraltar here, this is southern Spain, Portugal is now down here. So this is real time. This is how it would be if you were looking out of the window there. It would take you 90 minutes to go around the planet on the space station. So let's try to put some scale into this, to try to make sense of this vast planet we live on, and then move out into the solar system. So if we start with the Earth indeed is round, as our spacecraft show us. It's not flat. And this was a picture taken by the Rosetta spacecraft in 2009 as it flew past the Earth on its way to Comet 67P, which we'll come to later. So how big is the Earth in this picture? Well, the Earth is nearly 13,000 kilometers in diameter. So again, if you're a 2-meter tall human being, it's very hard to see that curvature. Move away, you can see it. So that's a very big number to begin with, and now I'm going to talk about the planets and the stars and the galaxy. So we have to make a model. We have to scale things down to size, and I'm going to scale the whole universe down. I'm going to shrink the Earth and everything else by 100 million. You might think that's a strange number. Why not a billion? Why 100 million? That will become obvious. So we're going to start with 100 million to 1. And that means that the Earth now shrinks down to 13 centimeters. Factor of 100 million from 13,000 kilometers. So it's something this big. And if Katia will now come up on stage, we actually have a 13 centimeter Earth. Okay? It's like being a magician, as you will now see. So, now what we're going to do is bring that little ball called the moon, and that moon is there. Now, of course, that's too big. The moon is quite a bit smaller than the Earth, so we'll scale it down. So now to scale, the Earth is 13.5 centimeters, the moon is 3.5. But the question is, where is the moon in that picture? Now, who would like to volunteer? Nobody in the front row, because I know you all know. Who would like to hold their hand up and tell me, if this is the Earth, how far away the moon is? Anybody want to guess? Nobody wants to guess? That's terrible. You either all know or you don't want to admit that you don't know. Well, it's actually not there. You know, you might think, here we are in Portugal, and maybe it's that distance away, or maybe it's a bit further, or maybe further away. I mean, you can see there's string on the ball. It has to go further, right? It's not exactly a good magic trick. So it's this far away. This is 400,000 kilometers, and the Earth is 40,000 kilometers around. So this piece of string was wound around the Earth 10 times. So the astronauts who traveled to the moon, they went a long way in a few days. So it's a lot further away, I think, than most people. Who says it's further away than you thought? Now it's okay, you can admit that. There you go. There you see, okay. So that's the magic trick for the day. Thank you, Katya. So if we do that now on the screen, which is a bit easier than it was with a piece of string, now you can see that that distance, that 400,000 kilometers, has now shrunk to that 4 meters. Okay, so divide by 100 million. So that's my scale model. We're going to use that for a little while now. Now, people have been there. I said the astronauts traveled across that distance. This is Buzz Aldrin being photographed by Neil Armstrong. You can see in the visor there on Apollo 11 in 1969. And later that year, Apollo 12 also went and touched down on the moon. And I chose this picture from my book because this actually shows a picture taken near sunrise on the moon. People talk about the dark side of the moon and the light side. There is no dark side on the moon. There's the far side, the bit you can't see from Earth, but it gets sunlight 2 weeks a month. This side gets sunlight 2 weeks a month. So there are times when the sun is setting and you can see the shadows. So at the top of the picture there, this is Apollo 12, and you can see the shadow of the spacecraft. If you look carefully, you can also see these little gray marks. These are the footprints of the astronauts. And this picture was taken in 2021. So those footprints are all still there because there's no weather on the moon. There's nothing to erase the footprints. And they're walking around this crater here. And if you look carefully, there's something here. And that something is another spacecraft that they landed next to called Surveyor 3. This had landed 2 years earlier. And the astronauts were able to land their spacecraft, Apollo 12, close enough to Surveyor 3 that they could walk around, touch the old spacecraft, and then break pieces off of it and bring it home. So I don't recommend this if you ever go to the moon. We have to protect these Apollo landing sites and so on, but NASA are allowed to bring their own stuff back. They wanted to see how being on the moon had affected the metal and the plastic and the glass and so on. So it was for the engineering purposes. So I really like this picture because these are almost the first space tourists. They went to a destination to see something that had been put there before. But of course, this adventure with Apollo ended just 3 years later with Apollo 17 in 1972. And this is one of the last pictures taken on the surface of the moon by humans to date. That's the rover in the background. You can see they landed in somewhat hillier locations after they learned the lessons of how to land more precisely on the moon. You can see the footprints and so on. So this is a kind of end of the first phase of human tourism in space. 1972. There are many people in the room who weren't even born then. And of course, we had the idea that this was the beginning of a great adventure. And of course, Stanley Kubrick in 1968 said, well, by 2001, we would have a city in the Clavius crater, and there would be people coming just on kind of trips to the moon. I hope some of you have seen 2001. My children hated it because it's so slow, Dad. It's so slow. It's the best film ever made, I told my children, but they don't agree. So the future didn't quite work out as quickly as we expected, but humans are now on the edge of going back to the moon with the Artemis missions, and hopefully European astronauts will be able to go. That's the deal we've made. At least we made it with the previous government in America. Let's see what happens with this one. So that's the moon for the time being, but now let's expand out further. And to do that, I can't get Katya to come on stage with an even longer piece of string. That won't work. Because the moon is the nearest thing to us. I don't know why I keep looking over here. I've got a clicker here. This is fine. So let's put things to scale in Lisbon. Okay? So this is where we are. You're sitting here in the pavilion. There's the Vasco da Gama Bridge. Well, you know Lisbon better than I do. What's the point of me telling you what's in this picture? But now let's put in that same model where the Earth is this big, 13 centimeters, and the moon is 4 meters away. Where is the sun? Where are the nearby planets? And that's to scale now. So we've put the sun here in this room. I know it's very dark. Imagine the sun is in this room. And the sun on my scale model would be about 14 meters in size. So it's 100 times more bigger than the Earth in diameter. So it would fill this space, the sun. And then we go out to Mercury, Venus, and Mars. It depends, of course. Mars doesn't even have a round orbit, a circular orbit. So sometimes it's closer to the sun, sometimes it's further away, but roughly 2 kilometers away in my scale diagram. So let's start with the sun and what the sun looks like to modern satellites. This is a picture from the European Space Agency's Solar Orbiter mission that was launched in 2021 and is flying very close to the sun and then comes back out towards Earth, flies close in again, takes very sharp pictures, but it's also measuring the particles coming from the sun, the wind, the gases that come away at hundreds of kilometers a second, and measures what the sun looks like when it makes big eruptions of gas that you can see around the outside. So we have fantastically detailed pictures. This is not what humans would see. You would have to see at ultraviolet wavelengths to see this. But this is what the sun looks like with all that energy bubbling up from underneath, from where the fusion power in the center of the sun is powering the outside. And if we zoom in on a very small area, this is a sunspot. Those tiny little dark areas on the sun, which if you use special glasses, you can see these tiny little dots, or if you project the light through a telescope onto a piece of cardboard, you can see the sunspots. And they're tiny little black spots. But this is as big as the Earth. So again, the scale of these things, which are moving constantly and changing over minutes and hours and days, is huge. And this is cooler gas coming up from underneath the sun. By cool, the surface of the sun is around 5,500 degrees Celsius. This cooler material is maybe 3,000 or 4,000. So it's still extremely hot, but it looks darker than the rest. So that's the sun. That's the star in the middle of our solar system, which brings all the light and the energy to the rest of the solar system, and of course the gravity that holds the solar system together. The nearest planet to the sun is Mercury. And Mercury is a very small planet. It's very dense. It has lots of iron in it. And it reaches a temperature on the surface of 450 degrees Celsius. It's the temperature inside a pizza oven. And this spacecraft you see in the foreground, called Bepi Colombo, a European mission which has gone to Mercury and has flown past it 6 times. And next year, Christmas 2026, it will go into orbit around Mercury. It has to deal with being next to a 450 Celsius object, and on the other side, the sun, 10 times brighter than here on Earth. So if you thought it was hot in summer this year in Lisbon, it's a lot hotter where Bepi Colombo goes. So our technology has to be extremely advanced to allow the satellite not to melt, basically. So these are pictures taken from Bepi Colombo a couple of years ago. And pictures taken by a previous mission from NASA, which didn't go into orbit, but looped around it at large distances, called Messenger, shows us some amazing places on the surface where there's all this colorful material. The colors are enhanced a bit, but you see there are blues and yellows and pinks and so on. And that's where there is material like sulfur and chlorine and sodium, other things which shouldn't be on the surface of Mercury anymore. Mercury's too hot. Where's that material coming from? And we think it's coming from small holes that are punctured in the surface when it gets hit by meteorites, or even bigger, by asteroids. So Bepi Colombo is going to investigate that in much more detail and try to find out why this material is still there. It just doesn't make any sense. And then we come out to Venus, which is again, about 1 kilometer from here. And this is an ultraviolet picture of Venus where you can see these beautiful clouds. And those clouds are not made of water, they're made of sulfuric acid. So this is not a place to spend a holiday, probably. In the visible, the wavelengths we can see, this is just bright white. But that's a trick in astronomy or in space science we use all the time. If you look in different wavelengths, the universe looks quite differently. So here we can see the winds moving at many hundreds of kilometers a second, blowing around Venus. If you went down to the surface of Venus, you would see giant volcanoes. And we've learned in the last few years, these volcanoes are still erupting on Venus. We've seen from pictures of the surface taken from above, this is a radar image, you can see changes on the surface from one month to the next where the volcanoes have been erupting. And volcanoes are a big theme all the way through the solar system. There are volcanoes in many strange places. Venus has them. This is one which is very important to many astronomers. This is Mauna Kea. It's the tallest mountain on planet Earth. If you measure from the bottom of the sea, it's taller than Everest. And these little white dots in the center are all the telescopes which sit on the top of Mauna Kea. And so this is where I did my PhD a long time ago, looking, of course, that way into space. That's what's called a shield volcano, like the one on Venus. But the biggest one in the solar system is this one. This is Olympus Mons on Mars. And this is more than 20 kilometers high from the surrounding landscape. There's very little atmosphere on Mars, but there's enough water that in the winter you get frost in the caldera at the top of Olympus Mons. And what's really fascinating, we've now learned that all of this material here and here, this is a giant landslide which fell off the edge of Olympus Mons billions of years ago, and it spread out. And by looking at how those ripples in the material are lined up, we know that that material must have fallen off into an ocean, into a water ocean on Mars billions of years ago. It wouldn't have moved the same way without the water to help it flow away from Olympus Mons. So although today Mars is a very dry planet, occasionally we see clouds over the tops of the volcanoes down here and mist in the Valles Marineris and Noctis Labyrinthus here, these canyons filled with mist at certain times. Mars today, though, is mostly a dry, extremely cold, almost dead planet. But maybe there's life under the surface. Maybe there are microbes which formed billions of years ago, evolved, and we could still go and find them today if we go to the surface of Mars. And I'll come back right at the end as to how I think we should do that. But if you look from orbit, you see some amazing things. This picture is like graffiti, but this is where little, what are called dust devils, little mini tornadoes, have moved across the surface of Mars, and they scrape the surface, they remove the dust, and you see the darker rocks underneath. And so this happens over a period of months every year, and then in the wintertime, it all gets rubbed away, and then it starts again the next year. So these change every year on Mars, these little dust devils which scratch the surface. Some of you have seen the film The Martian, where Matt Damon gets stranded because there's a big dust storm. It's nonsense. The atmosphere on Mars is so thin, only 1% of the atmosphere on Earth, you don't feel the wind at all. It's enough to scratch the surface, but it wouldn't blow a spacecraft over. So it's good Hollywood, but not actually true. Of course, we have rovers on the surface. This is the Curiosity rover. There's also Perseverance, and in the past, Spirit and Opportunity. And they've been able to drive around interesting locations to search for water and the possibility that water changed the surface of Mars. None of these machines so far have been able to properly look for signs of life. And the European ExoMars mission, which we hope will launch now in 2028, is designed to drill into the surface 2 meters, pull soil up, and look for possible signs of life in the past, or maybe even life still living under the surface today. So Mars is a huge fascination for many people in terms of the search for life in our universe. But we need to move further out. We need to move on with our journey. So this is where we were before, within a few kilometers of the pavilion out to Mars. But this is only a fraction of all the planets in our solar system, of course. We need to move out to the giant planets now, and to do that, we need to go much further away. So now this is Lisbon in the middle, and if I have my geography right, then Sesimbra, where I was yesterday, is down here. Very nice fish, by the way. So this is the scale we need to be looking at for our next part of the journey in the solar system, because the giant planets are much further away. This is the orbit of Mars, the red line, and then Jupiter. Between Jupiter and Mars, we find the asteroids, or many of them, and then we have the famous Saturn with its rings, and then what we call the ice giants, Uranus and Neptune. So these are up to 30 kilometers away, 45 kilometers away in this picture where the Earth is just 13 centimeters. So I mentioned the asteroids. What does a big asteroid look like? This is a big 100-kilometer lump of rock left over from the birth of the solar system. And this is an asteroid called Lutetia, and it was flown past again by the Rosetta mission more than 10 years ago as it made its way out to the comet. So there are hundreds of millions of these objects, many smaller, that exist in the place between Jupiter and Mars. Maybe they come from a former planet that collided with something else. And we think some of these asteroids actually come from the hearts of planets which have gone away since. And then we have comets, which live in the solar system, and this is Comet 67P Churyumov-Gerasimenko, the one that was visited by the Rosetta mission. You can see this, it's getting close to the sun here. It comes past close to the sun every 6.5 years, and when it does, the ice underneath the surface gets heated up and expands away and creates what we call the coma. This material makes a comet bright when you see it from Earth. You also see how it's beautifully casting a shadow on the coma, so the sun is over here making a shadow on the gas and dust there. But we got much closer to 67P. We even landed on the surface. So this is the surface of that same comet seen by the Rosetta probe in 2014. And it almost looks like a kind of a nighttime landscape, maybe in the mountains somewhere. But you have to remember the gravity here is extremely weak. If you were to jump from the top of this cliff down there, it's about 150 meters, it would take you 20 minutes to reach the bottom. And when you reach the bottom, you would just go, that would be it. It wouldn't kill you or anything. Then if you decided you wanted to go back to the top of the cliff, all you would have to do is that. But if you did that, you would fly off the comet and never come down again, because you would reach escape velocity. So all of the things you think about that landscape are quite different because of the way that comet works. But we investigated in great detail, and it was a great adventure to go to this comet. And again, things that tell us about the birth of our solar system, because this is all leftover material from billions of years ago. So let's move out. This is Jupiter, the biggest planet in our solar system. And it has more than 100 moons of different sizes. It has 4 very big moons that Galileo discovered with his first telescope more than 400 years ago. The Great Red Spot is a giant storm which has been seen for those hundreds of years but is now shrinking. It's going away. So if you want to see the Great Red Spot, join with our friends here who have telescopes, because in maybe 50 years it will be so much smaller. Maybe it will go away. Maybe another one will come. So these are storms which come and go. They're not permanent features. One of the more interesting moons, the big moons, this is the moon Io, and it looks a very strange place. All of these marks of yellows and whites and reds, what are they? Well, remember I told you there are lots of volcanoes in the solar system. These are all volcanoes. And there's one erupting at the top of the picture. So this was a big discovery when the first flybys of this moon occurred. People thought, what's that? Is that another moon in the background? No, that's a volcano throwing material high above the moon. And all of the surface here is covered with lava, or the leftovers from lava. There's lots of sodium in there, which is why it's yellow. So this surface is constantly changing, and there are hundreds of volcanoes active every day. And that's because it's so close to Jupiter, the gravity or the tides of Jupiter are squashing this moon like a rubber ball, squeezing it and making it hot on the inside, and that material then rises to the surface and emerges in these volcanoes. If you go a bit further away from Jupiter, you get to moons which are covered in ice. So this is Europa, and this whole surface here is water ice, with maybe some CO2, some carbon dioxide and carbon monoxide, but mostly water ice. And if you look at this, you might say, well, look, are there any craters? The moon is covered in craters. Mercury is covered in craters. Many moons in the solar systems are covered in craters. Why isn't this one covered in craters? And it's because the water comes out from underneath. There is liquid water, oceans of liquid water, much deeper than on the Earth, maybe hundreds of kilometers deep. And that water rises slowly to the surface and moves things around, and you get it refreshes the surface, it cleans the surface. So you might get a crater, but 1,000 years later or 10,000 years later, it's been covered up with fresh water, or the big icebergs have all moved around. So Europa and Ganymede are two places which are really interesting. Ganymede is a similar moon. We know there's lots of water in their oceans. Is it possible that there is life in those oceans, deep under the icy crusts? So ESA is currently flying a mission called JUICE. Silly name, but it means Jupiter Icy Moons Explorer. And it's going to explore these moons, not to land on them, not to dig holes in them, but to try to probe them from above with radar and other instruments to see whether those oceans might be a place where life could have developed. Moving on, further out, the famous Saturn. And this is a beautiful picture taken by the Cassini mission in 2013. And what's fascinating here is that the sun is behind Saturn, and that's why the rings are illuminated from behind. But if you think about it, if you're standing all the way out at Saturn and you look back to the sun, you should also see other things like the Earth. And Earth is in this picture, right there, that little dot. That's Earth, that's you, that's everybody in this room that was around in 2013 at least. So that perspective, that tiny little speck, and some of the other dots in this picture are moons of Saturn, and if you then rise above the North Pole of Saturn, you see this, which is that crazy? How can you have a hexagon on a planet which is made of gas? And this has to do with very fast winds moving around on the North Pole of Saturn, and those winds try to move down towards the equator, and they move back again, like the jet stream on Earth moves during the year. And it turns out, with the gas on the planet and the speed of that movement, it makes a regular pattern. So this hexagon spins around with Saturn over the few hours it takes for Saturn to rotate. And this thing in the middle is a big hurricane, which is much bigger than Earth. If you put Earth in this picture, it would sit in the middle of that giant hurricane. Now, there are two really exciting moons of Saturn. People who love Hyperion, I'm sorry, that's in the book too, but there are two really exciting moons. And this is one of them. This is Enceladus. This is another very icy moon, extremely shiny, covered in water ice. There are some craters, but over here, there are no craters here, and that's because these cracks in the ice, this moon is small. It's only 500 kilometers across. So it's the distance, I don't know, pick something 500 kilometers. Is that Madrid? I don't know, maybe. So it's a very small moon, but these cracks here actually go down into the ocean underneath, and water comes out. We can see the water flowing out through these cracks on the surface. And at the moment, ESA is working on a mission which would fly through that water and collect it and measure it on board to see if there's life in the oceans deep under the icy crust. It's only a few kilometers thick, the icy crust here, and the ocean is maybe 50 to 100 kilometers deep, much deeper than on Earth. And the other exciting moon is this one. This is Titan. Titan is a very big moon, and it's the only moon in the solar system that has an atmosphere, a dense atmosphere. The atmospheric pressure on Titan is the same as on Earth. And there are lakes and rivers and rain on Titan, and you can see that in this picture here. These are riverbeds on Titan underneath all that dense gas, but it's not water. It's liquid ethane and methane. It's so cold out there that this is hydrocarbons, which are liquids, not gases, and they make rivers. And the Huygens probe in 2005 landed in a riverbed. These are pebbles in a riverbed. At other times of the year, liquid flows through that region. So this is an amazing small world, and there's a mission now called Dragonfly, which should go back and fly a helicopter around Titan, which is pretty cool. So we're going to skip quickly through the rest of the outer solar system. This looks quite boring. This is Uranus. This is what Uranus looks like, but it has a really exciting moon called Miranda. Miranda has the biggest cliffs in the solar system here. This is called Verona Rupees. These cliffs are 20 kilometers high. And you could base jump from those, and it would take you a half an hour to drop to the bottom. But then you would be moving fast enough, you would kill yourself. And you can't wear a parachute because there's no atmosphere. So you think twice about base jumping for Verona rupees. And then Neptune, a little bit more exciting with some clouds on the surface. But now we're going to skip all the way out to the planet that's no longer a planet. This is Pluto, which was flown past in 2015 by the New Horizons probe. It has great seas of nitrogen ice, not water ice, not carbon dioxide, not liquid ethane and methane, but frozen nitrogen. And then as we move further away from the center of the solar system, we come out to the most distant object humans have visited with a space probe. This is Arrokoth. This is what's called a Kuiper belt object, further out of the solar system than even Neptune. And these two things bumped together billions of years ago and formed this weird-shaped object, which is about 35 kilometers in size. And out in the same region at the moment is this very famous object. This is Comet Halley. Halley's comet came through the solar system many times, most recently in 1986. At the moment, it's way outside, it's beyond Neptune. It's further out than Neptune. But it will come back on my 100th birthday in 2061. So I hope to be around for that. Just wish me good health so I can see Halley's comet twice in my life. That would be fun. And recently, we've been discovering some very interesting comets which are not from our solar system, but from other solar systems, which have come across all of interstellar space, arrived at our solar system, and will leave very quickly again. This is the latest one, Comet 3I Atlas. It's coming through the solar system right now. This is a picture taken a couple of months ago. And you can see it's turning into a comet, and it will fly through the solar system at extreme speed, and then leave again and go somewhere else. Some people talk about these being alien spaceships. It's not true. They're comets. The most distant probe we have sent into space, though, is Voyager 1. It was launched in 1977, and it's still sending signals back to Earth, but it's so far away now from Earth. On my scale map, where Neptune was at 45 kilometers away, this is 225 kilometers away. It's beginning the journey to the nearest stars. So the question is, what about that? We can explore the solar system. What about visiting stars beyond that? Well, this is the nearest star to Earth, or at least the nearest star system. This is the Alpha Centauri system. This is Alpha Centauri. It's just over 4 light years away. It means it takes light 4 years to travel from that star to us at the speed of light. It's not the nearest one, however. The nearest star to us is in the same system, and it's there. It's that tiny little orange dot. Próxima Centauri. It's a little bit closer to us at the moment. We think it may even have planets around it, Próxima Centauri. So it would be cool to go there, right? It would be cool to visit. But in my scale model, where this is Earth, the moon was over there, Neptune was 45 kilometers away, Voyager 1 is 225 kilometers away, where are Próxima and Alpha Centauri? So this is Próxima Centauri, Alpha Centauri, on a picture of the Milky Way taken from the Very Large Telescope in Chile. And in that picture, where we've scaled everything down by 100 million, Alpha Centauri is 400,000 kilometers away, which means it's at the moon in the real solar system. Does that make sense? I've scaled everything down that the moon is 4 meters away, and in the same model, Alpha Centauri is at the moon, 400,000 kilometers away. It's crazy. I mean, the scale is so much larger. That's why I chose 100 million to 1. The nearest star to Earth is 100 million times further away than the moon. You can get to the moon in a few days. At the same speeds, to go to the nearest stars would take 300,000 years. We are not going to the stars soon with the current technology, or maybe any technology. So to look at the rest of the universe in the last few minutes, we need to scale again, because otherwise we're dealing with big numbers. So now I'm doing it twice. 100 million times 100 million is 10 quadrillion to 1. 1 with 16 zeros after it. So this is my new scale model. In that model, the Earth isn't 13 centimeters anymore. It's 1 nanometer. a billionth of a meter. And that's the typical scale that transistors on the best modern silicon chips have, 1 nanometer. Our whole solar system now is not 45 or 50 kilometers, it's the size of a grain of sand. We've scaled everything down again by that amount. And because we've done that, that now means that Alpha Centauri is just 4 meters away, because we did the same trick mathematically. We pulled it to the same place the moon was. But where's the rest of our Milky Way? This is our Milky Way galaxy. As we see it, the Milky Way across the sky. This is from the Gaia satellite. If we were able to fly outside the Milky Way and look down from above, it would look like this, with a bulge in the middle, these spiral arms, which have full of stars and gas and dust. And where would that be in my new model? Not my old model, but my new one. Well, here's Lisbon again. The Milky Way, scaled down by 1 quadrillion to 1, would be that big. And the sun would be somewhere on the way to Sosimbro. So that's the center of the Milky Way here at the pavilion. This is where the sun is. So that tells you it's roughly 26 kilometers in my new model, where the nearest star is only 4 meters away. The center of the Milky Way is 26 kilometers away. Are you getting lost? I'm getting lost. So what do we find when we investigate the Milky Way? We find clouds of gas and dust, these dark patches in the Taurus dark clouds here. And these are the places where new stars are being born. That gas and dust comes together under gravity and slowly builds new stars. And we can see that process taking place. Other clouds, this is a very famous one. This is the Horsehead Nebula. People will have seen pictures of this taken by the Euclid satellite. And there are weird, dusty animals in space. This is my favorite picture probably in the book, the next one. This one's called the Cosmic Bat Nebula, as you might imagine. This demonic vampire bat is just a cloud of gas. It's not really a bat. But if you were going there in your spaceship, you might get quite scared at this point. So this is a cloud of gas and dust making stars. And there are places near to us in the Milky Way, much closer than the galactic center, like the famous Orion Nebula, a place where there's lots of gas and lots of dust, bright, big stars lighting up all that material. And if we zoom in with the Hubble Space Telescope, we can see a few stars in this picture, but the dust in this region is making it difficult to see all of them. So if you use the James Webb Space Telescope in the same place, but now, as João talked about before, infrared wavelengths, we see thousands of young stars all forming. And this is a very small region. If our sun was here, Alpha Centauri would be over there. And that's empty space around us. So this is thousands of stars all being born, all just very young, 1 million years old, not billions of years old. But if we zoom into that picture, we can also see places where there are planets being born around the stars. These material, this gas and dust swirling around. You can't see the stars here, but you can see the material swirling around them, building new planets. Famous picture from the James Webb Space Telescope and from Hubble before. These clouds slowly get burned away by the light, the ultraviolet light from massive stars, which makes them go away until the stars are revealed. And this is Westerland 1, a giant cluster of massive stars, one of the biggest clusters in our Milky Way galaxy. All very young still, only a few million years old. And then, as they become more normal stars, we can go and look for planets. And this is a strange picture. You say, well, okay, stars. This is the first star. It was one of the very first stars to discover a planet by the planet moving in front of the star, making the star slightly darker for a few hours, and then moving around again. And it did that every few days. So that little dip said, there's something moving in front of the star. It's a planet. And with modern technology now, even the very best technology, we can begin to take images of these planets directly. You block the star out in the middle, so there's a very, very bright star there. If you can block its light well, you can see planets. And if we follow them, they actually move in orbits around. We can follow them moving around like our own solar system. But stars don't live forever. Stars ultimately come to the end of their ability to make energy in the center. They run out of fuel. And they evolve, they change, their envelopes, the outer parts expand, and they throw material away, and they form these beautiful big bubbles of material. So we're now able to see the death of stars. And sometimes they form these amazing geometric shapes, these shells of material as the star pulsates and ejects material in different ways. And if you have two stars together, you can even create spirals in space. So there are two stars buried in here, swirling around each other. And as one star burps and sends material away, the other star alters its orbit. And you can see this spiral going out from the center. So these are sort of weird, strange geometric things in space. Ultimately, the stars, the big ones, explode, and they make supernovae. They explode in just seconds and throw most of their material out into space. This is the Crab Nebula, which exploded more than 1,000 years ago. It was discovered by Chinese astronomers. Not quite 1,000 years ago, it was 1054. And so this material now that was inside the star for millions and millions of years has now been sent back into space. And slowly, over time, it will come to form new clouds and make new planets and new stars. So it's a form of recycling. The universe has been recycled, this material, many times. So we're going to move out for the last part beyond our galaxy. This is what the middle of our galaxy looks like, though, if you use a radio telescope and infrared. It's an incredibly violent place. The center of the Milky Way is in here. There's a giant black hole in there, but there are huge clusters of stars being born. Everything's much closer together in the center of the Milky Way, and it's a really, really violent place. It's very hard to see because it's far away and there's lots of dust, but if you use the radio wavelengths, you can see into the middle. Further away, we see clusters of more quiet stars sitting there, billions and billions of years old. Sorry, that's a Carl Sagan moment there, sorry. Billions and billions. This is a globular cluster of many hundreds of thousands of stars which were born at the same time as our whole Milky Way. And then we have galaxies going around our galaxy. This is what's called, I'm not going to pronounce it properly, I can say the name of the discoverer, Magellan in English, although I call it the Nubecula Major in my book, and if you want to know why, come and ask me outside afterwards why I decided to give it a different name. So this is a galaxy much smaller than ours, but it has some of the most intense star formation anywhere in our local neighborhood. This is the Tarantula Nebula, and millions of new stars are being born in this incredible region. And the nearest exploding star, the most recent nearest exploding star, is in that region as well. This happened in 1987, supernova which exploded. And astronomers who were observing then, they went crazy. Every telescope that could see it were pointed towards this exploding star. We haven't had one in the Milky Way, our own galaxy, for hundreds of years, and we should get one at some point. So maybe you're lucky and you'll see a supernova, because nobody has seen a supernova in our galaxy for hundreds of years, but it should be happening. And so now we're going to move into the realm of the galaxies just to finish. This is a picture, night sky picture with the moon, and if you've been to a dark place, the furthest you can see away in the night sky is what's called the Andromeda Nebula. It's a galaxy, the nearest big galaxy to us. It's very faint, and with the naked eye, you can just about see a very faint patch of light. But it's actually quite big, and if you use a telescope to look at it, it will be that big on the sky. It's much bigger than the full moon. So this is a galaxy quite close to us. But where is it in my scale model? My scale model of Lisbon and the Milky Way has the sun 26 kilometers from the center. Where would the nearest big galaxy to us be in that same model? Well, we have to zoom out again, because it would be in Budapest, 2,500 kilometers away. But you could kind of see, this is to scale, so these galaxies are quite big objects relative to the space between them. And they're surrounded by much more material. And so this is the Andromeda Nebula, a beautiful amateur picture taken recently, with all of the young stars being born in it. Sometimes these galaxies in the middle form enormous numbers of stars and blow all this gas and dust away at high speed. So this is Another galaxy like Andromeda, but now there's lots of star formation around the center of it, blowing these huge fountains of gas and dust away. So our Milky Way looks kind of like this from above. The bulge, the center, we live out somewhere here, far from the center, with all of these arms of gas and dust. But not all galaxies look like that. Some galaxies are much more boring. Where's all the gas and dust gone? This is actually, we think, one of the biggest galaxies in the universe. It's 1,000 times larger than the Milky Way. It's a giant elliptical galaxy. All that light you see there is stars. You can't see the individual stars, but all of that light is stars. There's very little gas and dust. And that has got that big by eating all the other galaxies around it. Because galaxies crash into each other. They're not that far apart, and over billions of years, they actually collide, as you see in this picture. These two galaxies, a very big spiral and a smaller one, are passing next to each other. Galaxies don't actually hit each other. They will go straight through each other, because the stars are too tiny to hit each other. They're too far apart and too tiny. So the galaxies pass through each other, but the gravity will pull the galaxies apart, as you can see in this RP282. Sometimes you get amazing patterns like this, where the gas and dust is drawn into these crazy sinusoidal structures. So the galaxy which made this shape has been swallowed. It's inside the other galaxy now, but its gas and dust has been spread out. Sometimes the stars get spread out in ripples. The stars move away from the central galaxy. It's like dropping a stone into the pond. You throw one galaxy into another one, the stars ripple out from the center, and that's all of the shapes you see there. And then in some cases, we have galaxies where they hit so hard, all the energy starts making new stars along in the gas and dust that's been ripped away. Galaxy clusters get enormous. They're some of the biggest structures in the whole universe. So these are thousands of galaxies, each one with billions of stars in them, spread out. This is called the Perseus galaxy cluster. And this is just a small part of another much bigger cluster. So when you're out in this domain, the scale becomes impossible to understand. We also know the universe is full of material which we can't even see. Dark energy and dark matter. Dark matter has gravity. It can make things move under gravity, but we can't see it. Dark energy is a repulsive force, moving, stretching the universe larger every year. We can map it indirectly. This is a picture of the dark matter in the center, the red stuff. It's not a direct picture. It's a model which shows you where it should be. And we've built a satellite called Euclid to measure dark matter and dark energy, and it's surveying the sky, taking hundreds and hundreds of pictures every hour. So we're nearly at the end of our journey, further out into the universe. Because gravity also does something quite amazing if you bring too much material together. You can make a black hole. You can make it so strong in its gravity, so intense that even light can't escape from it. And at the center of this galaxy, M87, right in the very middle, is the first picture we have of a real black hole. This is hot gas just about to spiral into the black hole, which we can't see because the light can't escape. And this was made with a telescope that spanned the whole Earth from Hawaii to Spain, a giant telescope linked together with computers to take this image of a tiny piece of the sky in M87. And that gravity can bend light, even of other galaxies like this. We can see all of these curves, these arcs. That's all due to gravity in here, bending the light of galaxies much further away, far through the screen. And then the ultimate thing we are doing is looking further away from Earth and further back in time. Because the further away you look, the longer it has taken light to get here, the further back in time we're going. And these are some of the deepest pictures of our universe taken with the James Webb Space Telescope. There are a few stars in here, but everything else is a galaxy. All these little dots are all galaxies at different distances. And as you go further away, they get fainter, they get smaller because they're further away, but they're also further back in time. And with the James Webb Space Telescope, we're trying to look for the tiniest tiny dots in this picture to see if they were the first galaxies that formed after the Big Bang, 13.8 billion years ago. This universe we live in has not always existed. It's been around for 13.8 billion years and is expanding today. So in this picture, we're looking so far away, we want to see those original galaxies. But we can see the Big Bang itself. The echoes of the Big Bang from 13.8 billion years ago fill the entire sky at radio wavelengths. This is an echo of a time when the universe was much hotter. That universe has expanded away from us, and we can still see the faint light coming to us from different distances as the universe continues to grow and as time continues to pass. So these ripples here, all of these tiny, tiny ripples of maybe 10 millionths of a degree in temperature today, which we can measure, these are where those giant galaxy clusters form. All of those billions of stars in thousands and millions of galaxies, all formed out of these tiny changes in gas density billions of years ago. So in my model, to finish, where is this? In my model of the universe, we've said that the Earth is currently a nanometer. The whole solar system is a grain of sand. The center of the Milky Way is 26 kilometers away. Andromeda is 2,500 kilometers away. In that model, where is this? It's at Mars. It's 50 million kilometers away in that model, where the center of the galaxy is only 26 kilometers away. The cosmic microwave background is all the way at Mars. So to finish, why Mars? I said at the beginning that Mars is perhaps one of the most exciting planets for people interested in the search for life in our solar system outside of Earth. Did life manage to get a foothold on Mars billions of years ago and still survive under the surface, primitive life? This is a very exciting question, and I think that means there's very good reasons to try to send astronauts there as scientists, to go and investigate this cold, barren, very dangerous world. Of course, this is a science fiction documentary. This is a desert somewhere on Earth. On Mars, there's no water. There's nothing to breathe. There's radiation coming from space through the very thin atmosphere, and it's minus 50 degrees Celsius. It's a very dangerous place. Some people will tell you they're going to go and live there. Soon, next year, give me money, I'll take you to Mars. Of course, it's the story of science fiction. This is from The Expanse, where Mars is being terraformed. I know some of the people that wrote this series, some of the actors in it. They know it's science fiction. There are very rich people on this planet today who don't think it's science fiction. Science fiction has been an interesting topic, of course, for many, many years. Even back in 1908, people thought by now, or even in the Victorian, we'd have flying cars. Well, we're not quite there yet that we have flying cars. So there are scientific reasons to study the universe out there, and I hope just very briefly I've given you some pictures of what the universe looks like with the most modern telescopes, the most modern space systems. And my book is written as a tour guide, as if you could go there. But it's a fantasy. You can't go to most of these places. You can go to the space station if you're very rich, or you get selected as an astronaut from ESA or from NASA. You can maybe go to the moon, maybe the youngest people in the room, maybe. But to go to the stars, to colonize Mars, it's a fantasy. And I think maybe a dangerous fantasy. Because if we look at this last picture, this is looking back down from the International Space Station. And of course, right now, we are here. This is the pavilion in Lisbon. But at the same time, we are physically here. We are also here in climate change. I know you had a hot summer. We had a hot summer in Germany as well. And I'm Celtic. You know, anything above 20 degrees is bad for me. This is what's happened to our climate since the 1970s. This inexorable rise, 1.5 degrees above average. We're there already. And that shows no signs of changing. So although I hope it's worth looking out into space to look at the universe that we live in, for me the most important thing is to use that knowledge and to use that understanding, that curiosity to look back at this planet, because it's the only one we're going to live on, or if we're unlucky, die on. So I don't mean to end on a down note particularly, but the fantasists who sell you space as human destiny, the way we're going to go, they need to think about this and stop playing games, frankly. We will continue to look out into space. In a few years' time, this giant telescope, 39 meters across, will be finished in the Chilean desert and will help us look further into space. But hopefully that will help us learn more about what it means to be human in the universe and to be a little bit more humble about the short time we have on this tiny planet in the great darkness of space. Thank you very much. I should say, obrigado.
Is there any questions? Can we have a bit more light in the room, please? Thank you. Porque assim eu não vos vejo. Estamos ali uma. Se quiserem fazer em português, eu posso traduzir, se quiser.
Thank you for the outstanding talk.
Thank you.
My question is the following: with what we know presently about the space and the death of stars, can we really know what will happen to the Milky Way when our own sun dies?
So it's interesting because it comes back to the topic I just mentioned. People will often tell you, we need to leave Earth because the sun is going to die. Yeah, 5 billion years from now. Remember that the human race is 300,000 years old. Most species die after a few million at best. So we don't need to worry about the sun expanding. Trust me, don't add to your list of things to worry about. You've got plenty to worry about, which is real and happening today. The sun dying is not an issue. But the sun will die, and these planets will be here still. We won't, but the planets will be. So when the sun dies, it does a weird thing. It doesn't just kind of shrink down and stop producing energy. In the last millions of years, so a very short time compared to billions of years, it will expand enormously. It runs out of hydrogen fuel in the middle and starts burning the other materials inside, which it's made. It burns its own ashes. So it will start at some point burning the heavier elements, helium, which it makes from hydrogen, and that will actually cause it to expand into a red giant. And that red giant will reach out to Earth. It will be that big that it will sweep over Earth. So if you were unlucky enough to be an evolved cockroach living here in 5 billion years, your life would get very hot very quickly, because it's quite a quick phase. You don't have, it doesn't happen overnight, but it happens in millions rather than billions of years. And in fact, I've been thinking about if we wanted to leave a message here in the solar system that we were once here, a kind of memento mori, you should at least put it at Jupiter. Don't leave it on Earth, because Earth will be completely destroyed. But the time scale it's weird. It's 5 billion years from now, but the universe is already our sun is quite young. It's only 4.5 billion years old. The universe is much older. We could go to stars today and perhaps find planets which are 10 billion years old, much older than our own. So leaving a message for the future, of course, it's an artistic gesture, not a scientific one. So we do know very well what will happen in the solar system. At the same time, because later on the sun will lose a lot of its mass, it will form these big planetary nebulae. That gas will expand away. So the sun will become less massive. That means it has less gravity. That means the planets will move out as well. So all the planetary orbits will adjust. And we think that's happened in the past for other reasons, billions of years ago. But yeah, the planets will slowly drift away from, they won't go out of orbit, but they will move further away from the sun. I hope that was
it was very enlightening. Thank you.
Yeah, exactly. You're supposed to throw it. Okay.
Well, thank you very much. I just noticed that you mentioned that a memento mori would be an artistic endeavor. In that perspective, what do you say about the the materials that were sent in Voyager to outer space. What is the real message of those pictures and sounds that were sent?
The Voyager one, sorry, the Golden Record. Yes. So for those who don't know, the Voyager probes, which were launched in the 1970s, Carl Sagan and his wife Ann Druyan were asked very late, actually only a few months before launch, whether they could compile a series of sounds and images, and they put them on well, weirdly, the young people in the audience will know this better than the old people, on an LP. Vinyl. No, it's not made of vinyl. Everybody like my age, CD, it should be on a CD, right? Or it should be, anyway. So they put lots of these signals, and it was done very quickly, and it was done partly with a degree of cultural bias, let's put it that way. I think Carl was very sensitive to this, but they only had very limited time. I actually have been involved in a project called the New Golden Record, where we've been talking about bringing together musicians and artists, and this is partly linked to my work in Space Rocks. What would we send today? And it's a really difficult challenge, how to represent human culture. Because it's like Wikipedia, people want to edit the history to suit themselves. So what you would put in there, how do you do that democratically in a way that makes sense, that is unbiased? And again, what we thought we would do is not send it into outer space, far from because Voyager is just going into the emptiness. The chances of it ever being discovered are tiny. Our idea was indeed to leave it in orbit around Jupiter, because if you come to the solar system billions of years from now, you might go to the planets and look for stuff there. You'll find that more easily than if you send it. So I think it was a really important cultural gesture, and it's had a resonance. But it's not, people say it's a message to aliens that discover it. Not really. It's a message about us saying, we were here once, this is us. You know, and it's really about the message we send to the universe, not anybody contacting and coming here. There's the whole thing about the Fermi paradox, and we can talk about that. Are there aliens elsewhere in the universe? The one thing we do know is we're here, and that has some meaning. Even if it has no meaning on the timescales of the universe and the scale of the universe, it has meaning to us, and we should represent that in some way. Of course, we paint paintings, we build buildings, and they will all be gone. There's not much left of the Greeks and the Romans, right? Just a few ruins. That's us in a couple of thousand years. Think about 5 million years from now, or 10 billion years from now. How do we leave it? It's not important to anybody else. We were just bacteria crawling on the surface of the planet for a while until we killed ourselves. But, sorry, I'm a bit of a pessimist, as you might imagine. But it's important to us to represent that. That's what art is about. Life is about more than baking bread and buying shoes and watching Netflix. It's finding meaning out of this brief moment. And I do it, I suppose, through looking out into the universe. Other people do it by making music, by talking to their friends, by playing football. Whatever it is, we're more than just ants running around. So again, I think it's an important gesture, and maybe we should think about how we do that a second time.
It's more a message to us.
Yeah,
I think Carl Sagan was very sensitive to the ways of the world. I think if he had survived to today, he would be very, very sad about things are going.
Sagan is mentioned more than once in my book for a good reason. Carl Sagan, yeah, he is my scientific hero. Even though if he wasn't a Nobel Prize winner, he had a way of thinking about the way the universe is. Billions and billions. He had a lovely voice as well.
Yes. Thank you.
He never said billions and billions, by the way. That's a legend. He didn't actually ever say that. But he wrote a book called that. But
Hello.
Hello.
At the beginning, I have just say that I'm not a scientist. I see myself as a curious visitor.
Okay.
So I hope that my question will suit you as well. I'm always wondering, the origin was a Big Bang, as you said. What's your personal opinion as a scientist? What was before? And if you think that already this kind of universe could happen before the Big Bang?
Yes. How long do you have? Well, in some ways there was no before the Big Bang. Time started in this observable universe at the Big Bang. So this question of what came before it is a strange one. And let me illustrate that by one of the weird things that happens in black holes. when you look at somebody falling into a black hole, if they're unlucky, they fall towards the black hole, and as they get closer and closer, if you can see their wristwatch, or you can watch how they're moving, they will seem to get slower and slower and slower. And they never actually cross the black hole. You will never see somebody fall into a black hole. For them, they fall in. It happens completely. But think about what that means. You never see them fall in, but in an equally real universe, they fall in. So this doesn't make sense to monkeys, right? That's why we only know this for 100 years from Einstein's relativity. Time is a very strange construct. It's linked to space. There is no time separate from space. It's what we call space-time. As my professor, Malcolm Longear at the university likes to say, space-time. Space-time, as quickly as possible. It's one word, space-time. So again, what our understanding of the Big Bang is that it is not a moment in time, but a moment in space and time simultaneously. Now, is there another set of universes that created from tiny fluctuations in the vacuum? There are lots of theories about whether there are parallel universes, whether we are just one piece of a universe. One thing we do know is that we don't see the whole universe. We see a bubble in the universe. And every day that bubble gets one light day bigger. You can see a bit further. The cosmic microwave background goes further. But we know there's a much bigger universe around that for various reasons, which I can't explain. We know that there's much more to the universe than that part. But are there parallel universes? Will our universe shrink back down again and collapse to be small and then rebound and start again? We don't think so at the moment. We think the current universe, from all of our measurements, will continue to expand forever. But will another universe arrive out of the vacuum somewhere else? And these are very existential questions to which we do not have answers, because they're almost impossible to test with making observations. So when you ask me what's my personal opinion, that's a bit like asking me whether I prefer lager or IPA. It's a very, because there's no truth there. There is no actual real answer to that question. So if I was to express an opinion on that, it would be picking one god over another, and I don't believe in any of them, for example. So I don't mean the question isn't important, because of course we want to have a sense of what came before, what comes after. But physics is a lot stranger than the monkey brain can appreciate. Even those of us who are scientists don't understand this stuff. Not at all. Anybody tells you they understand quantum mechanics, they're lying. They can do the maths, just like with relativity, we can do the maths. But this idea that somebody falling into a black hole, we never see it. It never happens. They're frozen for all of time on the edge, on the event horizon. They fall in and they get squashed. They're dead. But for us, they live forever. How is that possible? It's how the universe is. It's a very, very weird place.
So thank you.
You're most
and I'm
welcome.
sorry if it was a tricky question. But
No, not at all.
It wasn't
Not
the
at all.
meaning of it.
There is no answer to the question, so I couldn't get it wrong.
More questions? There in the back.
That one is far away.
Good throw. Good catch.
I was lucky. Thanks for the interesting talk.
Thank you.
My question goes about your last slide regarding climate change,
Yes.
I believe.
Shall we go back?
No, it's fine. I was just curious about what's your opinion regarding the future. I see that the red lines are increasing over the years, and you presented data for Lisbon, but I believe other cities might have even more impressive.
Actually, Lisbon is one of the worst cities in
Is it?
Europe. Yes.
Okay.
I played around this morning. I went to the world.
Yes.
The world is now 0.9 degrees, global average. Lisbon is 1.5. And the northern hemisphere tends to be higher. The further you go away, everywhere's heating up.
Right.
But as the further you go north, and if you go to the Arctic, it's an absolute nightmare.
Yes.
So Lisbon isn't great, I'm afraid.
So you believe technology allied with satellite data and AI can revert this impact that climate change is causing us, or there is no future for that?
There's two answers to that. Could we use technology to avert the worst problems of climate change, to turn to clean energy, to low CO2? Yes, we could. We know exactly what the problem is, and we know exactly how to solve it. This is not a crisis of a lack of technology, although the investors will tell you, give me lots of money and I will solve it. It's not that difficult. I mean, okay, turn half the lights off and we'll do our bit, right? It's a cumulative thing across lots of behaviors and lots of things that we do as humans. The other question side of the question is, will we do that? And I see no signs whatsoever that we're making enough progress rapidly. I know you didn't mean it this way, but AI is a massive climate change problem at the moment because it's using enormous amounts of electricity and resources and water to run so you can say, hey, tell me how long it is to the next Taylor Swift concert. It's like, Jesus Christ. I mean, every one of those queries on AI burns lots of energy, and it's not all clean energy. So they're beginning to talk about, small nuclear power plants, but at the moment, it's the same energy mix we're all using. It just comes from the grid, and that's still a lot of CO2 in it. So I've been told by my wife, when my kids were younger, not to talk about this because it scared them. I think it's true. I think we have to be very careful how we talk about this. Not that we should hide from the truth, because if you give complete despair about the future with climate change, we will all give up and do nothing and just, go, Rome is burning, let's go and have a drink. We have to take action and we have to work together, us. Yes, we have politicians, yes, we have billionaires, but it's us, it's normal, ordinary people that have to get together at the community level and say, enough of this, right? It's not easy, we see that, we see populists winning today. One of my favorite bad stories is that science communication, and there are people here in the audience who are extremely good at science communication. We've become enormously better at it in the last 20 years. At the same time, we're failing because half the population denies science, denies the reality that vaccines will help you through major diseases or avoid them, that climate change is happening. These are not stupid people. I want to emphasize that. They're being propagandized. People are making money out of exploiting people's fears and their anxieties about the future. How do we cross that divide? We've become so polarized. We don't have discussions about it anymore. We have people throwing bricks at each other. So I don't know what the answer to this is, but it scares the shit out of me because it's happening and we are not doing enough. Not at all. And I'm a hypocrite. I took a plane ride to fly to Lisbon, right? This is Al Gore. When Al Gore was giving his talks, an inconvenient truth, people said, but you're a bad man, you fly on planes around the world giving your talks. You have to weigh the balance, I don't know if my talk will change anybody's mind, because hopefully you all get this message already. Why aren't we giving this talk on the street to people who are saying, I want to vote for the right wing because they're going to make everything well and they're going to give me a magic pony and they're going to get rid of all the people who don't look like me. All of that stuff is going on at the same time, and it's terrifying, right? Climate change is the biggest issue facing us, and we've got a moron across, are we live streaming? Yes, we are. We've got somebody across the Atlantic who is just trying to bring the planet to an end. It's utterly terrifying. I'm afraid I don't have any optimism at all at the moment. But again, we know what we have to do. It's not magic. It's not how do I travel to the nearest stars, invent a faster than light machine. We know exactly what to do. And we're not doing it. Why? It's not the lack of technology, it's the lack of human compassion and human will and the laws that let billionaires get away with propagandizing people. All of our social media, all of this, take your heads out of your phone. I'm talking to myself as much as anybody else. Anyway.
There's a question online.
Oh, okay. Is it Donald?
No.
Sorry.
I'm not sure because of GDPR. I'm not going to say that. So I would like to explore that question further. So the question that we had here at the front. If there was nothing before the Big Bang, how were the conditions brought together for such a unique event as the Big Bang?
Well, again...
Are you going to say you don't know?
I'm not going to say I'm going to know, because the thing about the Big Bang is people visualize it as an explosion that happened in a room. Right, that we set off a firecracker in the middle of the room there, that there was a pre-existing something and the universe grew into that. I know it doesn't make sense, but the universe did not exist for there to be space for the universe to have an explosion and grow into. What was it before that? Was it a piece of a vacuum in another universe that then reached the conditions? Because this stuff in front of you here, actually this is full of air, but if you went into space, that vacuum is full of particles creating and dying away on tiny fractions of a second. They come, they go. Humans don't see it, but you can measure it. You can do experiments which show that there are particles being created and disappearing constantly. And the conditions could arise 1 in a trillion, bazillion, gazillion times that it actually runs away and expands. This doesn't make sense to monkeys, right? It makes sense if you write it down and do the equations. But then somebody says, well, what's it like? It's like, I don't know. In the same way, I don't know how quantum mechanics allows, if I close my eyes, there is a finite chance that when I open them, you've all gone. It's true. You could do the calculations. There is a finite, non-zero chance you have all disappeared. The chance is extremely small, and I do this on every talk, and it's never happened. But it's not zero. And how is that possible? How is it that you could all go through that wall? But at the quantum level, we can make measurements of particles which can't go through walls suddenly appearing on the other side. Because there's a finite chance, and if you fire enough particles, it can happen. How does this make sense? So I'm not answering the question in that way, but it's a challenge for us to try to talk about a universe coming out of nothing, because that uses time. It came, what was before. These words don't apply in our understanding. But also we can't study it because we can't even get that close to the Big Bang past the cosmic microwave background at the moment. With gravitational waves, primordial gravitational waves, there are ways of getting closer. The inflation epoch of the universe, when the universe went from the tiniest size to the size of a football in 10 to the minus 37 seconds. What the hell happened there? How did that happen? These things don't make sense, but we observe the consequences and we see it. This universe is deeply, deeply weird. Go home with that in mind. It is not a sensible place at all, the universe you live in.
Talking about weird, I have a question. So if there was a supernova right now in the sky, what would we see in the Milky Way? The one you said we haven't seen yet.
Well, the first thing you would see is the neutrinos. So the middle of the star would belch out vast numbers of neutrinos, and if it was close enough by, they would get here before the light got here. If it's far away, neutrinos don't travel quite at the speed of light, they might get here a bit later. So that wouldn't be visible to us, it would be visible to detectors underground. But if a star within Betelgeuse, right? If Betelgeuse blew up, and Betelgeuse is a few thousand light years away, it would get extremely bright extremely quickly. So supernova 1987A was, 55 kiloparsecs, 26. So, 10 times further away than the center of the Milky Way, and that's already a lot further than the nearest stars. People just saw that. They went out and went, oh, what's that? That's new. Astronomers, because it wasn't super bright. But it could easily be a daylight object, and we think that historical supernovae were seen in daylight in the past. So it could overwhelm the brightness of the sun, and there would be a bright star in the sky for a few days. It wouldn't make a noise, though. I mean, if it's happening now and we don't know about it, just go on social media, see if it's happened, because it's not going to make an explosion that we hear or anything. It's bright light in the sky. Now, if it's incredibly close, and we think that there's no stars near enough to us to be a supernova danger, which would then hurt the Earth, because there's an enormous amount of fast material and radiation. If it was kind of the next star over, one half of the planet would be dead very quickly. The other half, at night, in the daytime, wouldn't see it, or whenever. If it happened on the side of the planet you're on, you'd be dead, and the other side would go, what happened to Fred in Arizona? He just disappeared.
Thank you for your talk, Mark. Is it on?
Yeah.
Okay. Mark, I had one question. You showed a lot of images in your presentation, and the question I have is, do you still think that there is a role for astronomical images? Do they still have the power of the Earthrise or the blue marble? Or have people become numb to all of the beautiful images that nowadays anyone can see on their smartphone?
Oh, you've exposed my biggest fear in life, because my career has been about making beautiful images from space. You're asking a slightly leading question because you're a spaceflight fanatic. I don't think that astronomical images of Orion or the Milky Way are any less spectacular than pictures taken by humans who went to the moon or are in space. So I wouldn't compare them in that way. But the world is full of AI videos of stuff moving. Even NASA and ESA do this occasionally. We take a static picture. We're at one distance from Orion. We can see slightly in 3D because the Earth moves around the sun, and on one time of the year we can see from this side and that side, but the angles are so tiny you can never see a proper stereo picture. Occasionally people then kind of fake it and say, well, if these stars are this distance, we could imagine a movie where you would be flying through space. I don't like those, but I can't deny that people like to watch cat videos and celebrity videos where they're not just cat. It's a moving cat. So people like movies, and in space we have that challenge that our images are essentially static, and you can kind of zoom into them and do the Ken Burns effect and so on. So I have worried about that, and in particular, even selling a book with pictures in it. Do people read books? I hope you're going to prove me wrong, by the way, but do people read books? I do, but I'm old. My kids, hopefully we've raised them that they read books, but you just know that's not how most people get information. So I've read a recent article about the power of art galleries and why a gallery of a static image on a wall is much more than just absorbing an image. It's about going into a space, not big space, a space, and contemplating what you take from that. Now, maybe that's a minority of people that have the time and the desire to contemplate what this thing might tell you, but it's a different way than watching a movie. You appreciate it in a completely different way if it is actually static. Now, the one thing I'm going to say is that one thing we do cheat with is the colors. Not in a bad way. It's not false colors. We're not lying, but we amplify the brightness. If you went into space and you went to the Orion Nebula, or you went to the Andromeda Nebula, Pedro knows this because I told this in front of a whole bunch of people 10 years ago and they all screamed at me. The Orion Nebula doesn't get any brighter as you get closer to it. It gets bigger. But you look at the wall over there, right? That wall, if you walk closer to it, the amount of light should increase by 1 over r squared. As you get closer, it gets brighter. But it gets bigger at the same way. So the wall doesn't get any brighter as you get closer to it. So the human eye, if we were standing next to the Orion Nebula and it was filling the sky, it wouldn't look like my pictures to a human at all. It would be faint and gray. It's not bright enough to make those colors. So we already are involved in mediating the images, but there's that philosophical issue that I ask myself very regularly. Are we on the verge of losing the contemplative power of space images, of art gallery images, of a beautiful landscape that doesn't move, right? Rather than show me the motion, show me it all, and give me it in 10 seconds so I can scroll to the next one. And I think the human brain is being hacked by social media in that regard. Maybe that's not the question you asked. Maybe you...
No. That was more or less if you still believed in the power of astronomical
I fundamentally, deeply believe in it because I know what happens to me. It's happened, fortunately, 10 times in my life. You sit at a telescope, maybe the telescope is 1 million kilometers away, but you suddenly see something that no other human being has ever seen in history over 300,000 years. You're the lucky person. And that's the privilege of being an astronomer. We have access to all these amazing machines that you pay for and you let us play with. And we get to be the first people to see something that no human being has ever seen. And it's an incredibly emotional experience. It lasts maybe 10 or 15 seconds. It doesn't I don't know how to describe it. It's weird, almost a taste in your mouth about, it's an astonishing thing. So, and I hope that privilege can be there for people even seeing it, as being the second and the third and the fourth. Once it's saturated, maybe that image has no power anymore, but the universe is big and there's amazing things to be seen. You see that with JWST. Hubble has been observing for more than 30 years, and JWST has changed it again. So I deeply hope that to be true, but it goes with my general anxiety about the state of the human brain and how it copes with the world we live in. Because we were just meant to live in little tribes, few people, relatives, friends. We're not made to live in millions of people, right? Our brains are 300,000 years old in programming terms, and how we cope with progress. I know I sound like some kind of ancient person who wants to go back and live in the country and so on, but I think it's really screwing people's brains up, particularly social media and the rapidity of information access. It's doing something bad to us, I think. So I would hope we can somehow go back without losing everything in the meantime. There's a little metaphor. A few years ago, we had the option with our Herschel mission. Herschel had finished its mission, and people said, well, what do we do with it? Do we move it away from the Earth, or do we crash it onto the moon? Because if it went away from the Earth, it might come back again in 300 years' time. I said, move it away, because in 300 years' time, we'll either be developed enough to go and get it, or we'll be living in caves going, oh, pretty lights. So I think this is many people have said this before. I'm sure the Romans did, the Greeks did, the Elizabethans, everybody at some point in history said, everything is changing too quickly. But the difference this time is climate change. It's changing the entire planet at once. It's not a local problem in Portugal or a local problem in China. Many of our historical problems were regional and local. The people on Easter Island that used up all the trees and then suddenly had nothing to live by, so they died out. This time it's global, and that's new for humans. We've had global crises before us before, and we're making this one, and that's the real stupidity, right?
On a positive...
Let's maybe finish here. In 1 or 2 minutes, we are going to ask you to go outside, but before that, I'm going to ask Anna to come on stage, because we have a little token of appreciation to you, Mark, because I think everyone knows how much you love fish.
I was going to say, is it a fish?
This time, this one is not grilled.
Thank you very much.
It's, you know that sardines are the typical from Lisbon.
Yes.
It's a sardine.
It's a sardine.
I can tell, it's a sardine.
It's not often I get given a sardine after.
Yeah, but open it to show what it is. It's a sardine, but it's a spacey sardine.
A spacey sardine? Are the sardines going to succeed humans?
Yes.
I mean, I have to say, I don't eat octopuses anymore, because I think octopuses are going to take over the planet. They're pretty intelligent. I don't know. I'm baffled by applause, because Portugal as a nation eats a lot of octopus, right?
A lot.
But a Lisbon sardine as well.
Yeah. So you like fish? It's a sardine.
There we go. It's a space sardine. Is that a cuttlefish? I don't. Is it? Thank you very much.
Not to eat grilled, this one.
So this is one stop, so that's the name of this talk. Next stop, the universe. So to be continued. So we invite you to continue your journey through the universe by buying Mark's book outside and contemplating all these beautiful images, and also having a small cocktail with us that is served outside. And in the meantime, also, if you want to see the exhibition that is out there, we are invited to do that. And also, Rui is here if you have any questions.
But before you leave, because I know I talked about the evils of social media, but you do it for us, because you're great at selfies, right? That way I can well, with everybody in the room here, just... I don't know, I won't post it, I promise.
You want me to?
Yes, because she's young, she's good at selfies.
I smile, he doesn't.
Yeah,
You have to smile as well. Well, it has to be like that.
Thank you very much.